So today we're going to talk about how to use first-order logic to develop realism-based ontologies. And actually, I'm going to demonstrate you how to do that based on what we learned over the past 2 days. So just as a reminder, you remember, if you were here in the previous sessions, how we come to ontologies by looking at reality. Okay, on the first day, I explained the logical principles. Yesterday, I explained the ontological principles. And today, we are going to put them together to make a tiny ontology. So we are going to do that on the basis of the Common Logic Interchange format, or CLIF. Again, as a reminder, take, for instance, this sentence: John is going to Boston by bus. So you could represent that by using first-order logic in the CLIF format in what I would call the mainstream representation. Mainstream representation being predicates, they express properties and relations. So in this case, for instance, the statement is translated as there exists an X and a Y, and all this is the case. What is the case? X is a goat, John is a person, Boston is a city, Y is a bus, X is the agent of, John is the agent of X, Boston is the destination of X, and X is the instrument of Y. Or the other way around, Y is the instrument of X. The different colors here, they indicate the various elements that you can use in first-order logic expressions. So quantifiers in yellow, variables in green, predicates in orange, individuals in red, and connectives in purple. You see only one connective here, but other connectives are or, if and only if, and not. So this is the mainstream representation. We are going to use also the realism-based principles. And this is an example of a CLIF axiom in BFO 2020. So the assertion is no role changes type during its existence. And in a realism-based representation, you have only predicates that express relations. Almost. There are a few small exceptions that I'm not going into, but we don't use properties in a realism-based representation. We use only relationships. And then the transformation of this assertion into first-order logic using realism-based principles is this one. We are going to work on an example that I also gave yesterday. It's a tiny fragment from the International Classification of Headache Disorders, namely the notion of persistent idiopathic facial pain, which is defined as persistent facial pain with varying presentations. Now, that is a little bit ambiguous, okay, because it could mean different things. So at the level of the types, we need persistent facial pain, and we need a couple of presentations, each of which are different. If we look at instances, we can think of 3 different patients. Okay. So all of them have pain. Okay. But one, which I call my pain, has persistent facial pain, but always of the same presentation type 1. Her pain is such that it is always persistent facial pain, but one time it is of type 1, another type of type 2, another time of type 3, and so on. What I mean by presentation types, that are types of pain like throbbing or aching or dull, and so on. And his pain is always persistent facial pain, but always of presentation type 3. Mm-hmm. So persistent pain has also been represented in the National Classification of Orofacial Pain, which uses the International Classification of Headache Disorders. You have the reference here. Okay, so it is defined there completely as persistent facial pain with variable features recurring daily for more than 2 hours per day for more than 3 months, in the absence of clinical neurological deficit or preceding causative event. So here you see the diagnostic criteria. we are not going to cover them all. We are only going to cover these three. Okay, facial pain fulfilling these two criteria. And of that criteria C, we are only going to look at dull, aching, or nagging quality. What I'm going to use for that? Well, a couple of tools. One is the CLIF template in the way that it has been designed specifically for BFO 2020. And also a tool, the complete set, you can find it. Let's quickly look at it. So here is the BFO 2020 webpage. Okay, there you find the common logic part here, and these are all files which contain these axioms. There is another interesting tool. This one here has been designed by Alan Rittenberg last week, and it's really really neat. I started to use it since. So this gives you all the CLIF axioms of the BFO. Okay, and you can search for them. You can see how they are organized. For instance, if you want to know, okay, what is all in history, or where is it all used, you click on history, you get all the axioms related to history and so on. We are also going to use a Prolog program that I designed over the years and that I use for my students in a couple of the courses that I teach. That program takes CLIF templates which filled out with axioms and then does a couple of things with it. For instance, checking whether the first order logic is the way that it should be. It can transform it in different kind of other formats. And also it can connect to a theorem prover. And the theorem prover that we are going to use is prover 9. So if you are interested in that, I provided a link. Here is the web page. There is a recent update. Okay, so prover 9 exists already, I think, 30 years almost. It has been available on various platforms. The development stopped in 2009, but then it has been taken up maybe 2 or 3 years ago, but only available under Linux. So I'm not using that one. I'm still using the older Windows version. So I don't need to mess with different operating systems. And all this works together in a pipeline. And the pipeline is what you will see here, and I will shortly explain that. Are there questions thus far? Is the goal for today clear? Okay, let's then start. I'm going to close my PowerPoint. I don't need that anymore. So what do we have here? So here we have the parser, which is a program in Prolog. That's the symbol for SVI Prolog, which is from the University of Amsterdam, and it's freely available. I have a batch file, which also uses the parser and then makes a connection to the prover 9. I have here a demo plan that I created, and that is specifically for this presentation. So it allows me to just copy things that I did before and put it in the CLIF template so that I don't need to type everything. What we are going to work into is this little thing here. So this is how a CLIF template looks when it is empty. So it starts with a comment in which you can add some title. Then it has a title which you can add whatever you want. Then it has a field text which encloses everything. It starts with an out discourse that should contain the list of relationships that you are using in your axiom. And then in here, we will write all the axioms. Now, to make everything work together, we need also a little bit of a setup. Okay, so the setup is such that we identify with what kind of tools the different programs need to work. So we have here an init parser tool. One is with the BFO, and another one is with no BFO. That is used directly by the parser. In the environment setup here, you also see that you have tools which use BFO and init and one that doesn't use it. Okay. So, and it's important because we're going to start the example by not using BFO. So pure whatever you design as an ontology, and then later on we are going to fill in we are going to use the BFO axioms on top of what we are designing today. So to do that, I need first change this extension here. That's the one which uses not a BFO. I didn't go far enough. There we are. And we can start working. So the first thing that we need to do is, of course, say, okay, we need the first axiom. And the first axiom is going to be, how is persistent idiopathic pain organized? So I replace this part here with what I already prepared. So this is the axiom. It simply says every persistent idiopathic facial pain is an idiopathic orofacial pain. You need to follow a certain syntax within the BFO 2020 template. Namely, your comment has to be between single quotes here, and at the end, between square brackets, you put some index. So you can decide how you want to call that index itself, but the index needs to be for all axioms different. Okay, and then here you have the main part in CLIF, and this one simply says for all P and T, if P is an instance of PIFP, which is the abbreviation for persistent idiopathic facial pain, then it is an instance of IOFP, which is idiopathic oral facial pain. Okay? So this is a simple axiom for which the counterpart, if you are used to binary relations in OWL or using Protégé, it would be subclass. Okay? So when you have that there, you can run the parser by simply clicking on it. And the parser will generate various kind of outputs. So let's look at some of them. Okay? One is a comment file. Okay? So in this case, of course, we had only one axiom. It's very short. It gives a couple of warnings. So it says, okay, there are two terms which are rarely used. Okay? Well, what is that? That's because the parser keeps track of the number of terms that you are using, and you can give the parser the instructions in the init file, at what moment you need to be informed about terms that are not often used. Now, why is that? Because it might contain spelling errors. Okay? And this is one of the mechanisms that when you make a spelling error, okay, which is something that cannot be detected by the logic, of course, but it can be detected by using certain heuristics on the file that you write. The parser checks also for whether there might be inappropriate quantification. Okay? It also checks for pure literals. Now, why does it do that? Pure literals, they are totally useless in theorem proving. Now, in this case, we have, of course, only one axiom, so let's look at it. The pure literal in this case is IOFP. What is a pure literal? It is a literal that is not further used in any other axiom. So if you can conclude on the basis that because something is a PIFP, okay, then it is useful, of course, to know that it is then also classifiable as an IOFP, but about IOFP, nothing else is known. So it's interesting to know, but the reasoner can't do anything further with it. So you want those kind of things only for your top class. Okay, if you have more of those empty literals, then yeah, there might again be a mistake in your axiomatization. Not necessarily, but it might be the case. And then it gives also the details of the warnings. So in this case, it has those two terms which are rarely used, and it will indicate in which axiom that is. Another thing that the parser do in the conversion is giving suggestions for writing the axioms more concrete, more succinct. Now, in this case, there is no very short axiom. There is, of course, no suggestion to do that. What you always need to do is look whether the parentheses are balanced. So whether when you are using CLIF axioms, use an editor, okay, which shows you which parenthesis matches with which parenthesis. So in this case, you can see that on the red color. For your own sanity, okay, try also to use an indentation in the appropriate way. And use your closing parenthesis always at the very end. So then is it very easy when you use your cursor, you put it at the end, and you go from right to left, you will see whether the parentheses really close where they should be closed. So in this case, everything seems to be okay. Are there any questions? No? Okay, so then I'll add a little bit more.
Actually, Dr. Hustis, I have a question. So when you have for all P and T, is it presumed that T is a time? So you're saying for all P at time T, or is T just anything?
No, nothing at all. So in this case here, we are absolutely not saying what T is, right? We are only saying something about P. Now, our interpretation is indeed good, that we mean it that way to be, okay? So in this case, you are reading it in the way that I intend it, okay? But for the logic, of course, you need to explain that, and you will see that indeed there are axioms in the BFO when we include it that explicitly says if you have a statement such as instance of P, PIFPT, then P is this and T is that. Okay,
so then if you have the statement if is instance of P, PIFP, I'm not sure what the T, like what's the meaning of the T in this statement then?
In this statement, it is about time. But only me and you know that.
Oh, right? I mean in terms of the CLIF, like I would have assumed that this is just, it only takes two arguments. Like if instances of P, PIFP, I'm not sure what a third argument does in that case.
That's the time. That's what I explained yesterday.
Oh, yeah, but I'm saying in the syntax of the language, I mean.
In the syntax of the language, it's such that you have your relationship and then you have as many arguments as you will need. Okay, there is no limitation there.
Okay.
Yeah. So, and in this case, yes, we decided to take instance of here with three arguments. No, it's a very pertinent question. Okay.
All right, thank you.
Okay, so I add a couple of things now. So I'm going to build up further the hierarchy. Okay. So here we said that every PIFP is an IOFP. Okay. Here we say that every IOFP is a facial pane. And again at the time. So the correct reading, to be totally clear, is that for all P's and for all T's, if P is an instance of IOFP at T, interpreted as a time, although we didn't write it yet, okay, P is an instance of facial pane at that time. Okay. We see also that this one is a little bit more elaborate. Okay. Every facial pane is a pane. So what does this axiom says? Okay. It is every facial pane is a pane, an instance of pane, but also there exists an F. And F is an instance of a face at time T, and P is located in F at T. Okay. So here we use the connectors if and and. Okay. So, and with and, you can have as many expressions in there as are needed. Again, you check whether the parentheses are okay, and everything seems okay in this case. Okay. Now we can again save the entire thing, and we can run the parser. We run the parser, and the parser says errors found. So in that case, only a comment file is generated. What you need to do is look at the comments. So the comment file is here. You get here the warnings, and here is the error. Located in is a constant used as a predicate, but not declared in out discourse. Oh yeah, we forgot it. All predicates need to be declared in the out discourse segment here. Now, why is that? Because CLIF by itself, okay, doesn't provide any rules or no identification of what counts as a relationship and what not. It's the user has to define that. So if you indeed say here, located in is a now discourse term, which is the term that they use to say it's actually a relationship, then you are okay. So if you run the parser in this case, the error should be gone. And it is indeed gone. So there are a couple of other files that are generated and which are interesting. So let's quickly look at some of them. One is a Kowalski file. I explained that on Monday with the transformations. So for each of those axioms, a set of Kowalski rules are generated. You can ignore this. This is indexing information that is used by another reasoner that I use. So the first axiom led to one rule. Okay, you see it here. The second axiom also. The third axiom leads to three rules. Three rules which all have the same antecedent or premise, and then a conclusion, which is a single statement. Okay. Now, this kind of rules are used by provers and by theorem provers and by other kind of systems. For instance, if you want to link it with instance data and to do reasoning. But it is also interesting to look because the format of those Kowalski rules is actually much simpler than the axiom. Compare it with this. So if you are good in first order logic, this should not pose any problem, but it might puzzle a little bit, right? Well, if you look at the Kowalski files, then they look way more simpler. And personally, I use that quite often to see when an axiom doesn't do what I expect it to do, then quite often you can see the problem by the oddity in one of those Kowalski rules. What also is generated is a vocabulary. Okay, so it lists you all the terms that are used, in what context they are used. Okay, you see the relation instance of here, how it is used over all the axioms. It checks whether there are inverse relations. So we didn't make any inverse relation, but later on we'll demonstrate where they come from. Antonymic relations. And again, here the pure literals. You remember in the beginning there was only one. Okay, now we have several pure literals. Yeah, and it is normal because the last axiom, we didn't link it to anything. We didn't say what the face was. We didn't say what located in means, and so on. Clear? Then let's move on. What we also can do is look at a couple of mistakes. Okay, so you need to know first order logic to a certain extent, at least the syntax. You can make mistakes against it. For instance, imagine that you would have made, you put here in parentheses too much. Okay, and you were still working and you had one too less here. When you look now, you still have balanced. Everything is still balanced, okay? And you go over it and you see we are fine. But actually it's not, because what you see normally from here, you should go to the consequence, but you drop that immediately there. Now imagine that you wouldn't have noticed that. And you run the parser on this example. You get an error. The comment file, again, will tell you what the error is. Okay. And see, you have it here in the third argument. If is a logical connector used in this axiom with the wrong number of expressions. Yeah, indeed. Because we closed the end here. So actually there is now one expression directly under if. This is the second one. And this is the third one. Okay. So when you have a good parser, okay, it's able to identify those problems. Another one that we can use is related to your first question. Okay, imagine that you have here instance of, and you remove the T. Let's check the parser. Errors found. We know that we then need to look at the comments file, and it's indicated here. So it tells you, oh, in axiom 3, instance of has in this axiom an unusual number of arguments, 2. While 6 times in your axiom-based it is used with 3 arguments. Well, indeed, look at it. We had instance of here with 3 arguments, with 3 arguments, here with 3 arguments, there with 3 arguments, there with 3 arguments, and here we have only with 2. Well, that's likely a mistake. Now, why does the parser in this case give that mistakes? That's in the initialization file. We have explicitly said that we do not allow relationships with the same name to have a different number of arguments. Now, logically, there is nothing wrong with that. You can do that. Okay, now simply that relation has a different signature. And you can do that. But it's easy to make mistakes in that case. Okay, so in this case, we set a parser. Okay, do not accept that. And there are many more of those kind of oddities that can be detected. And while I'm giving this demonstration, probably many more will come up. Questions? All right, let's now continue. We are gonna now add something. We want to check whether our logic adds up. Okay. So when we have defined axioms that says that the PIFP, and I'm going to use the shorthand expressions, that the PIFP is an IOFP and an IOFP is a facial pain, and a facial pain is a pain, then it should follow, right, that a PIFP is a pain. Well, how can we check that? You can make your proof manually by looking at those axioms and doing your transformation, but it's way easier to use a theorem prover. Okay, so to do that, in the system that I'm using, you prefix, okay, the identifier by the word theorem, and with a hyphen. And if you do that, okay, then the information that is given to the theorem prover is automatically this, that all those axioms here need to be taken as assumptions, and that this axiom is something that the prover needs to prove. Now, to make the prover work, we don't use the parser. The parser doesn't anything there. The parser has a little bit of low-hanging fruit reasoning, but it's not a theorem prover. Okay? So therefore, we have this file here, which is a batch file, which first calls the parser. The parser generates a file, which it then, through the batch file, is transmitted to the prover. So let's click on that. Voila. So here that was prover 9 at work. So in the first part, you see you get exactly the same thing as the what you get through the parser here. It's called, it generated the output files. It identified that it has to prove a theorem. Okay. And then that's the output by prover 9 here in this case. Gives you again what was tested. Okay. And then displays the proof. So a proof in this case that consists of 13 lines. You can read this proof. There is no need actually to do that. If you are really interested in how the system solved that problem, you can do so. The important part is that you look here at the axiom supporting the proof, and whether you get here exactly what you expected. And that's indeed the case, right? So you see the 3 axioms, which all together should lead to this theorem, are indeed referenced here, and the theorem itself as well. And therefore, we can accept that the theorem is indeed, the putative theorem is indeed a theorem. Now, what does that mean? Well, strictly speaking and logically, it means that you do not need to keep this in your axiom set, okay? Because it follows from what is already in there. However, if you are using it for reasoning or for theorem proving, it might be not bad to keep it in there because it might speed up certain proofs of more complex things. While in other situations, it might slow it down. So there is no certainty there whether it is beneficial or not. You have the choice, and it is on the basis of your experience that you can tell, okay, this axiom, I always see that proofs go better, so let the theorem in it, and others you remove. So that's one thing that you can do with it. You can also use the system to work with instance data. So let's remove this theorem, and I'm going to add two other formulas. Okay, so these two here. So what are these? They say, okay, what if we tell the system that there is a certain person, John, okay, and John has a pain, and that pain of John was yesterday a PIFP. So that would mean actually that John's pain yesterday was also a pain, okay, for the very same reason as that axiom there. Okay, that is the logical consequence of those three things. Now, would it work? Well, we do that indeed in this way. So rather than testing a theorem, we're giving instance data, and here a very simple example here, and now we ask a question by letting the theorem prover actually know that he needs to try to prove this as a theorem. Okay. So let's save that. We run again the theorem prover, and yep, indeed, there we have it. So there is the proof that you can follow, and you see we've got exactly the same information as before, okay, except that now also the scenario is added, and that of course the theorem, we gave it a different index, it's a different theorem that has been proven. Questions? Okay, let's proceed. Go back to our set. So, notice here you need to be careful in CLIF with your comments. So in this case, I used the standard English Jones, but because the requirement is that comments need to be enclosed in single quotes. If you use a single quote like this, it screws up the syntax, right? So therefore, you need to use this exception slash, okay? When you precede a single quote or a double quote by a slash, okay, then the parser knows that it indeed is not the end of the comment, but that it needs to go to the first single quote, which is not preceded by such a slash. I'm gonna remove this. And let's add two others. Another example. It's pretty close to the previous one. So we use actually the same scenario. Pain of John yesterday was a PIFP. So now we ask the question, well, if it's the case that there exists a time at which the pain of John was a pain. Okay, so that's different than what we asked before. Okay, so today, before we asked whether John's pain was a pain yesterday. Okay, now we are asking, is it the case that there exists a time? Okay, so we use it now, the t here, as a variable. And if we ask that question on the theorem prover, it should indeed tell you that that is the case, that such a time exists. Voila. There you have it, using exactly the same arguments as before. Now, how do we know what that time exactly is? Well, the theorem prover will not tell you, but if you analyze the proof, then you can see it actually that it is here. Okay, so you have here the statement that he came to the conclusion that the pain of John was an instance of facial pain yesterday, while we asked here the A, okay, the T is here replaced by a capital A because we are using here the prologue form of variables. By the way, you might be surprised why we get at the end here that empty. The $F here is actually empty. Well, that is because this theorem prover works actually by not trying to prove directly the theorem, but by proving that denying the theorem gives you an inconsistency. Okay, and that has to do with the fact that for first order logic, there is no known algorithm that can tell you for sure that an axiom fits completely in the set of axioms that you have, but there is a known algorithm that allows you to tell you that if there is one that doesn't, that tells you there is one that doesn't. Okay, so that's why these theorem provers they use by testing the satisfiability. And if it is not satisfiable, then they will find it. Now, it doesn't mean that they will find it very quickly. Okay, so there is an algorithm that is guaranteed to give it to you on the condition that you give it unlimited time and unlimited space. Okay, so but for smaller axiom set, that is usually not a problem. But when we go towards the end of the demonstration, now you will see indeed that it might become a problem at some point. All right, let's expand. And please, any questions, shout out, okay? Now we are going to add a little bit more complex example. So I have now this scenario. It's again a scenario with instance data. Pain of John was an instance of pain yesterday. The face of John was an instance of face yesterday. And the pain of John was located in the face of John yesterday. And the question is, does there exist a time that the pain of John is an instance of a facial pain? Okay. So what do you think on the basis of these axioms? Will the theorem prover say, yes, there is such a time and that time is yesterday or not? What do you think?
I don't know for sure, but I'm going to guess yes.
Okay. So best way is to try it out. Take the theorem. And you see search failed. Okay. So it's not the case. Now the interesting part here, I said so, using the satisfiability, there is guaranteed an answer. Okay. But if you don't get an answer, you don't know whether it is unsatisfiable or not. Okay. Here you don't get the answer, okay, but clearly it says SOS empty, okay. That means the set of support is empty. This means that the theorem prover actually tried all possibilities that there are in those axioms and that those possibilities are exhausted, okay. And this means indeed, okay, it cannot be proven. So in this case, you are sure. When you get here timeout, okay, then it is because you set a parameter. And I usually set my parameter high enough. So in this case, it's 900 seconds. That I say that's about 15 minutes. So if you don't find it after 15 minutes, don't bother any further. And I can't wait. I need to proceed. Okay. Now, there are other theorem provers. Some of them are faster, like Vampire, and there is Z3. They all work on similar principles, but using different heuristics, better optimized, and so on. Okay. But the time might be an issue. But in this case, if you see source empty, you are sure it cannot be proven. So why is that? Well, the problem, well, it is actually not a problem, but it is here in this axiom, okay? So what we, in this axiom actually explains what it is for something to be a facial pain, okay? You have to read it from left to right. So if P is a facial pain at T, then this is the case. But what we were doing here was actually giving a number of data, and we asked him, can you infer that P is a facial pain? Or in this case, that John's pain is a facial pain. Can you infer that on the basis of the axioms that we have? Well, there is no axiom that actually states here, if you go from here, that you may conclude that. Okay? This axiom doesn't say that. So to do that, we need actually to add the other one, another one, okay? Or we can do something else, but let's simply add it here. So we say now, okay, definition of facial pain, if and only if. So we have here the if and only if, and we don't change anything on the previous one. So when you have an if and only if, then it should work in both directions. Let's test it. Voila, and there you go. So only on the basis of the scenario 2, FAP2, and the theorem, it is proven. Oops, I need to change something here. Okay. Now, there is another interesting aspect. Okay, let's look again at the comment file. So the comment file is from the parser. It has nothing to do with the theorem prover. And if we add axioms, you see the comment file get bigger and bigger. So we have the term rarely used here. We have the relations with the placement. And we have here, we see a partial overlap. Okay. So what it actually says here is that the parser identified already that one of the three clauses of FAP1 is subsumed by FAP2. Okay, so axiom 5 in PIF BC in our file is related in a certain way to axiom 6. And yeah, the only difference indeed that you have between 5 and 6 is that here is an if, and this is an if and only if, which then actually means that you wouldn't need anymore this one, okay, because this one is included in it. Or in terms of logic, actually, this one should be a theorem, right? This axiom should follow from this one. So let's do that. Let's check it out. We put it on the top. Okay, I was uncareful in pasting it there. We don't need the scenarios anymore. And now we need to put here theorem in front. And is it, here is another issue that I need to remove. Okay. Activate the theorem prover, and voila, there we go. It is indeed a theorem. Okay, so that's the question that we asked. So we can remove it. So you can develop your ontology like this, okay, completely independent. What we are by using the realism-based principles, okay? So we are still using the realism-based principles, but we are not using some other ontology or another ontology that we want to borrow from. So that's what we are going to do now. To do that, I'm going to switch those init files. So this is the one that doesn't use BFO. Let's change the name again. And I'm going to remove this part here. Okay. And I need to do the same thing for the reasoner, for the prover, sorry. No BFO. And this one, the BFO. So let's just look for inside this file to know why I'm doing that. So these are all the instructions that you give to the parser on how to operate. Okay. So you have the project name, BCP for Bootcamp thing here. And here you specify which ontologies to use. Okay. And in what way? So we say here, okay, use the BFO. Use also a BFO extension. Okay, which is the one that Alan Ruttenberg and I designed by working on our paper about change. And then you have the scenario that you are using here, which is specifically for the bootcamp. Okay. So that's why we change the name there. Now, I'm not going to change anything else. By simply run this file here again. And now do it with the inclusion of the BFO. So let's start with the parser here. So you see now, it takes way more time. Okay, it parses all those different files. It does some lightweight reasoning. There are no mistakes. And we can look at the comments. You see, we have now way more comments. Okay, what is there? We have different kind of warnings. Okay, 23 in total. One is there, textual duplications of axioms, where it is indeed the case when you load the full axiomatization of the BFO, which comes in different files. Well, those files, they cover certain sub-theories. But some of the axioms, they are useful, or they are actually part of different theories. So they are actually duplicated there. Logically, that's not a problem. But again, if you are working with the prover, they need to be removed, okay, for efficiency reasons. It lists in this case also that certain discourse terms, okay, relationships that are declared are not used. Also, that is not a problem, okay. But if you intended to use them, then it might indicate a problem. It also tells you that there are some axioms that are very likely inappropriately quantified. Okay? You see the details later. What it detects here is whether clauses are generated from the axioms in which there are universally quantified variables which only happen in the consequent part. Okay, and that's sometimes that might indeed be an accurate representation of what is intended, okay, but in most cases it is not, okay, and it leads really to overgeneralization. And if you have those kind of axioms, then a theorem prover might make some conclusions which are actually not valid. So it is good to be aware of that. You see also that BFO contains certain clauses which again, they are logically correct, but they are not expressed in a way that is really concise, okay, which are run with a lot of redundant or tautological clauses in it, where it say if P then P, or where you have P and not P, okay. So they can be removed. So you see here, for instance, this axiom, 12 out of the 16 clauses that are generated, okay, are tautological. Which means that there is actually a much simpler and more concise way to write that axiom. So here are the two that are very likely inappropriately quantified, and Alan Ruttenberg and I are now already looking for a couple of weeks to see whether it is truly inadequate or whether it reflects unintended models. We are not yet out of that. It gives other axioms that can be simplified for other reasons. Okay. The parser check whether there is overlapping. So the parser itself detects actually direct theorems. Okay, so there are two axioms in the BFO which are theorems of one other axioms. So this is what I call low-hanging fruit reasoning. You don't need the theorem prover to do that. By inspecting simply the clauses that you generate out of the axioms, you can already detect those kind of things. And then also overlap. Okay, there are also two axioms that have overlap with other axioms. Here there are a set of axioms which generate clauses which multiple consequences. Okay, so you remember from the Monday that I said that there are 5 different types of clauses that can be generated out of axioms. One of them is if A and B, then C or D or E and so on. Those are very hard clauses to for a theorem prover to deal with. So if there is way to avoid to express things in such a way that you get those kind of clauses, it's worthwhile looking at it. And you see there are a couple of axioms here where 100% of the clauses generated are all of that sort. There are findings relevant for modularization. Okay, so the parser with the low-hanging fruit reasoner included in it detects inverse relations. So inverse relations are things like when you have defined A located in B at a time, okay, and the inverse is B has location A at a time. Okay, logically there is no problem with that, but it's a duplication of effort. And theorem provers, again, they need. Then first thing that they need to do is actually eliminate those doubles, or it increases their search space. Personally, I think that, but that's a personal opinion, that inverse relationship should not be in an ontology, but they are useful in a terminology. Okay, so it might be useful for users that they don't need to remember. Okay, if we need to specify a location, is it in the sense of being located in, or is it in has location? Okay. So if you want to give that possibility to the user to do it either way, so that's fine. But then before you save your axioms, replace the ones, okay, so that it is always in one direction. Also detect antonymic relations. So antonymic relations for theorem proving, they are also useless. Okay. So in BFO there are 2. So V1, for instance, is a particular, and if V1 is a particular, then it's not a universal. And also the other way around it goes. So there is no point of having those 2. Use systematically one. And then again we have the pure literals here. Okay, there is one such like entity. So BFO doesn't do anything with entity. When you have an occurrent and you have a continuant, then it says, okay, both of them are entities, but adding entity doesn't give you any more information. And then you have, again, the detailed files where all those axioms have one or other problem. And at the bottom, then you see here 2 axioms for which the parser itself suggests how the axiom can be rewritten in a more succinct way. All right. So we included the BFO, and now we are going to work further by adding more things. So one of the things that we need to do is to be a little bit more specific about some of the terms that we introduced. Okay. So we need indeed, under the realism-based paradigm, to say that PIFP is a universal, and IRFP is a universal, and pain is a universal, and so on. Okay. Now, universal is here a relationship. Okay. So this actually means that we also need to specify here in the out of discourse that universal is a relation. Now that we've done that, we are fine. And let's run the parser again. Okay, there are no mistakes. But now look at this. An extra file has been generated. Let's look at this file. This is the content of it. So what does this file actually do? One of the drawbacks, okay, of using CLIF or first order logic is that you must be as explicit as possible. And when you use terms, okay, which are individuals in your domain, like continuant and continuant fired boundary and face and facial pain, so they are individuals in your domain, you need to explicitly say that they are different from any other individual. If that is the case, okay, so logic allows you to put different individuals which are identical. In that case, it's again more a terminological flavor that you give to your ontology. But if that is not the case, you need to tell the system explicitly that they are all identical. Now that's of course a huge task, okay? Because that list grows. If I remember well, then it is the n multiplied by n minus 1 divided by 2, okay? The number of combinations. So if you have 37 individuals in your domain, then it is 37 multiplied by 36 divided by 2, and that's a number of statements that you need to say that they are different. Like continuant is not identical to face, continuant is not identical to facial pain, and that entire set, right? So one of the advantages of this parser is that it generates that for you automatically, and then the next time that you run the parser or the theorem prover, that's information that is added to the system as well. There is one other thing that I can demonstrate. Well, let's skip that. We are going to add now our couple of our terms that we introduced to the BFO. So I said we used the BFO. The only thing that we used of the BFO this far was that notion of a universal, okay? But we didn't link our terms yet to the BFO. So that's what I do now with these two axioms here, okay? So we say that every pain is a process, okay? Exactly in the same way, okay, by using this template. And when you are writing your axioms, it is very easy to make this kind of a hierarchy. You simply copy this template and then you change here your the names of the terms here to represent what it actually needs to be. Okay. And also the second one, we say that every face is a fired object part. Fired object part is one of those subtypes of material entity in the BFO. Okay, so now we have our pain, which was the highest level of the little ontology that we developed as far there, and face is also connected to the BFO, and the BFO is now completely covering everything that we have in our little demo ontology. So if we do that, then we can again run the parser. Okay, there is no error. It is never wrong to look at the commands file anyhow to see whether there is something, but there is nothing special that I can see, so we are good here. Oh no, there is one here. Okay, the axiom has the same identifier as at least one other one. So axiom 6 and axiom 3, and it is FAP2. Okay, what is the issue? We have FAP2 here, and we have FAP2 here. So let's simply change this into 1. And now I remember indeed, it was because we changed this axiom here from if to even if, but we added to it as a second axiom. So now this is gone. And let's now also use the theorem prover again. Okay, we didn't ask for any to prove anything, right? So you don't see anything here with the theorem. So we didn't ask anything specifically, but nevertheless, run it. So we run the theorem prover. First the parser. Parser detects no mistakes. And then the theorem prover. Voila. And we get a problem. Okay. Indeed leads to this. Read this here. So standard mode. Prover 9 is searching the ontology for 900 seconds for inconsistencies. Okay. If theorem proved is displayed, the test revealed an inconsistency. Now, where does this consistency comes from? Okay. The basis is any of those axioms here, right? Something here is not wrong. No, it's not right. Now, if you assume that it is not a BFO, it needs to be in the little ontology that we built, right? And the answer is actually at the end. When you find an inconsistency, okay, or the theorem prover find an inconsistency, the easiest way is also to always to go from the bottom to the top. And see what is the cause here of the empty literal, as it is called. So it is the combination of line 22 and 24a. So 22 says that something which is related to facial pain is a continuant at the time which is related to facial pain. And then 24a says that that's not a continuant. So that's indeed an inconsistency. And why it is not an inconsistency, okay, that's here because that same thing is an occurrence. So we have here a situation that our ontology says that something in there is both the continuant and an occurrent, and that is something that is not consistent with the BFO. Now, where does the problem come from? Well, if you don't know BFO really well, then you need to look at those axioms here. So those indexes here, you can try to find it in the proof, okay? Or you can use that, what is it here? The things here to enter. For instance, let's look at the MBF1. So you type here MBF. And then you see, okay, this is the axiom here, MBF for all U, if a universal, there exists the P and the T, that instance is P. No, that's not it. So you need to search to it. That's a little bit of detective work to do. But make the story short, the problem is actually that we used located in, okay, here, and that we used it for something in the first argument being a process. So remember in the beginning, we were just talking about pain and we didn't say what pain was. Okay? So we said what the facial pain was, but we described it in terms of pain. Okay? We didn't say what pain was. By linking now pain to the BFO as a process, it's that what causes the inconsistency. And the problem is indeed that the located in, okay, cannot be used when the first argument is a process. What we need to use there is occurs in. So we need to change that. So we have occurs in there. And we would write here also occurs in to be consistent. And we have occurs in here. And then I think we should be good. So let's try it again. And there is an error found. What might that be? Yeah, I'll use it in the beginning. Voila. Occurs in, as in this axiom, an unusual number of arguments. Okay. Oh, is that indeed the case? Well, let's look at the axiom. Occurs in. Yeah, here you have it. Okay, you see occurs in has 2 arguments, not 3. So we need to correct that. Where's our occurs in? Here. So we need to remove the time. Now, why is that? Well, it's because it is defined in BFO like that. It could have been defined in another way. It could have been defined with 3 arguments, but it isn't. So it is no surprise. Okay, so if you read the literature, and BFO has become like, I may not say a standard. So it has a certain user group. But in the biomedical world, it has received like certain recognition. So people like to say that they are compatible with BFO, while in many cases they are not, because they didn't try it out, okay? They might have built their ontology using the protege with the binary relations, but then you cannot find those mistakes, right? So when you use the full-blown first order logic, you can avoid those kind of problems. Questions? No? All right, so we are going to go further. So one of the criteria, if you remember when I showed the slides, was that you need to have different kinds of pain. Okay, so different presentations of pain. So I will now introduce a couple of axioms that introduce those different kind of pains. Well, quite a bit. So we have we were here, right? So we have the nagging pain. Okay, we say that every nagging pain at the time that it is a nagging pain is an instance of pain. We declare the universal. We define the dull pain in a similar way. That dull pain is a universal. We take the aching pain. Aching pain is a universal. Okay. And now we need also to say that those nagging pain and dull pain and aching pain as symbols are different. Okay, we don't need to say that explicitly. Normally you have to do that, but because we have that mechanism that can be generated automatically, we don't need to do it. But that is at the level of the symbols. Okay, so here we are talking about the things in reality being denoted by those symbols, which are different themselves. Okay. So nagging pain is disjoint with aching pain and dull pain. What it actually means is that if something is a nagging pain, it cannot at the same time be a dull pain, and it cannot at the same time be an aching pain. And we need to do that for dull pain to say that at the time that something is a dull pain, cannot be at that time a nagging pain or an aching pain, and the same thing for aching pain. So needs to be distinct. Again, you will see here, it's kind of very verbose, but if you want the logic to work, you have to do it, because there might certain conclusions that you want to reach, okay, might not be reached if you don't do it. Or what is even worse, that the prover might find solutions by saying, okay, yeah, this is indeed a theorem. Okay, when we assume that aching pain and nagging pain are identical, while actually we don't intend that to be. So that means that you get actually a theorem that can be proven, but on false premises. Premises which were not expressed, okay, but which are in your mind. So you need to avoid that. So now another question, and think about that. Do you believe or do you want to be it such that something which is a nagging pain now is a dull pain tomorrow? Remember, in the talk yesterday, I gave a couple of examples. So the specific example was actually that I was an instance of child in 1960, and I'm an instance of adult since 1980. Okay, so I changed type. Now, do you not think that it is possible that something which is an aching pain at a different time can be another type of pain? What do you think?
I think maybe it could be expressed that way, but I'm wondering, you also mentioned about like a disease course, having a bunch of like a lot of different instances of occurrences that make up a disease course. I wonder if it could be expressed more cleanly that way.
The example for the disease course was a little bit different, okay? Because what I was talking about is a specific instance, right? Well, it's related to it, but it's a little bit different, okay?
Okay.
So the best way to figure it out is, again, like, try it, right? So what we are going to do is putting a scenario in, copying it here. So let's put it on the top. So we take this scenario and we say, okay, the pain of John was a nagging pain yesterday morning, and the pain of John was a dull pain yesterday evening. And we give the problem to the theorem prover. Do you see again? Voila, and it is inconsistent. Okay, you can follow here the proof for why it is. Now, why is it inconsistent? There are here two BFO axioms that are used in the proof for the scenario being inconsistent. Okay, we need to check them. Okay, which of the two is it? So then we understand why it might be the case. So one is LSO. And LSO, oh, let's put the thing there, voila. For all Tx, if instance of X is a process at T, then instance of X is an occurrent. No, it's clearly not that. And the other one was AYR2, AYR, voila, here. No occurrent changes type during its existence. So that's the one. So what is in this? What is here the reason for the inconsistency? It's actually dictated by the BFO. Now, if you say, well, yes, but in my perception of the world, it should be possible, okay, that a pain sometimes is this and the very same instance of pain, right? At another time is something else. Well, if you maintain that, then you cannot claim at the same time that a pain is a process as defined by the BFO. So then either you need to move part of the BFO out of it so that you don't have the inconsistency, or you say, okay, I don't commit to pain as being a process, but I commit to pain as being, let's say, a quality or a realizable entity, something like that, okay? You have the freedom to do that, okay? I picked pain here because I've been working on a pain ontology for 12 years. No, I may not say that I've been working on it for 12 years. 12 years ago, I worked on pain ontology, and by talking to colleagues and so on, we agreed, no, pain for us under the BFO, it should be a process. If you disagree with that, you can define it as whatever you want, as a quality or as a realizable entity, or you can even qualify it as an entity which is not, for which nothing is represented in the BFO. It's totally to you. But if you use the BFO and you say it is a process, then you cannot have at the same time that instances of pain can change type. Okay? Is that principle clear on how you need to work with dictates, or some calls it dogmas, made by the BFO? So the dogma is processes don't change because they are changes. Okay? But there is no dogma that you, in the sense that entities which are not defined in the BFO, that you should define them as being processes or as being qualities or whatever. That is absolutely not the case. So that's what requires to you do a certain ontological analysis and then commit to what you believe that is the most accurate way. And it is usually science that tells you that. So remove that scenario. Now, if it is the case, okay, that no, I'm gonna keep that scenario and add this here. So if it is the case that that is inconsistent, then it should actually be a theorem, right? That and I need indeed to remove the scenario, or I keep the inconsistency. So nagging pain always stays nagging pain, okay? You notice that I here use another relationship here, exist at, that clearly specified at which time something exists. It's a relationship that we have not yet in our discourse list, so we need to add it, or the parser will complain. So this should be a theorem, okay? Let's try it. All right, and we are there, okay? And you see again also, it uses the two axioms from the BFO, the one which defines nagging pain and the one which defines pain as being a process. And again, we have there the AYR axiom from BFO, which is actually at the heart for why that would be the case. Cool. Let's continue. So now we need to refine that persistent idiopathic facial pain a little bit better. The only thing that we said this for was that it was an idiopathic orofacial pain. We didn't say anything else. We defined some subtypes, okay, from pains that are part of it, but we didn't say actually what it is. So now we are coming really in the nitty-gritty parts of our thing here. We need to remove this axiom, this theorem. I'm gonna add, no, I didn't copy enough. Okay, I added now 3 axioms, okay? So this adding goes fast, right? Now, I have to confess, writing those axioms, okay, that doesn't go that fast, okay? Not because of the syntax or whatever. I mean, I'm now quite well versed in using that first order logic syntax, but in getting it right in the way that you really express what you want to express, okay? So when you start an exercise like this, do not think, okay, that this axiom set that I copy and pasted here, that was developed in an hour and a half. No, it took me 2 days actually to do it. In part, of course, because I wanted to show you several aspects and be able to do that in an hour and a half. But it is hard work, and along the way, even if you are experienced, you make many mistakes, okay? But there is no shame on that. Okay? You are helped by technology, and you work until you get it right. So this deepening out of persistent idiopathic facial pain, the summary is actually like this. An IOFP is a PIFP if and only if every temporal part of P, which is a pain, is an instance of aching, nagging, or dull pain. Okay, that's the first criterion to remember on the slides. I think I have the slides still here. Yes, I do have them. Okay. It is dull, aching, or nagging in quality. And then the second criterion is it projects, and I wrote it as a PIFP compatible temporal region. Okay, so what I'm doing there is a little bit taking a shortcut. If you look at the criterion itself, so the criterion that I'm representing here is the B, recurring daily for over 2 hours a day and for longer than 3 months. So what do I then mean actually by a PIFP compatible temporal region? Well, that is indeed a temporal region which satisfies this requirement here. Now, you could also do it another way. You could make several axioms which actually work with numbers and hours and months and the natural numbers, and then you need to compute whether it falls in there and so on. This is something that you can do, but actually there is no need to. But in these cases, what you need to think at is how would actually a clinician who is filling out an electronic healthcare record, how would he do that? Okay. He is not going to fill out all those numbers, right? He will ask the patient, so when you have that pain, how often does that happen? And the patient will give him some answers. And then the clinician might ask, so if I understand it right, it is more than 2 hours a day and already since more than 3 months. And the patient will say yes. Well, if that is the case, okay, you can imagine that you have a well-designed electronic healthcare record where that is one of the questions, okay, that the system, okay, proposed to the clinician ask this, okay. And then if the clinician answers yes, then automatically that compatible period is entered in the logic that tries to reason with the patient data. Okay, so that's the reason for why I do it this way. So look at the axiom itself. It is a bit conditional. Okay, so it works in both directions, and these are the conditions. Okay, for that IOFP being a PIFP. So there must be a temporal region. The pain must occupy that temporal region. Okay, that temporal region must be an instance of a region that satisfies the temporal requirements for a PIFP, which is expressed in this one here. Okay, and then for all temporal parts, okay, if you have a part of that time, okay, there must exist a PP, which is a pain, okay, and that pain is a temporal part of the entire episode of pain. And so if that is the case, then that PP must either be one of those 3 pains, okay, and not another one. That's the semantics of the or in first order logic, right? It has to be one of those 3, or two of those three, or all three, but it might not be anything else. So if that is satisfied, okay, then IOF, an instance of IOFP at that time is an instance of PIFP. And as before, we need to set the saying that that temporal region that we defined is a universal, and say also that it is a temporal region. Okay, so with this statement, we actually connect it to the BFO. Now, why is that? Because we use other relationships here from the BFO, like occupies temporal region, and I think that's it, right? There's not another extra one. So we need to add that here to our list. Occupies temporal region. Okay. Is there an temporal part of here also? So one of the little tricks also that I use is when you add to your file more relationships, organize it alphabetically, okay? Because if the list gets long, right, then you might not find, oh, did I have that already or not? If you do it alphabetically, it's very easy to identify. If you make a mistake, no problem. The parser will tell you that there is a problem, but then you need to go back to your file and change it and so on. So it's better to prevent the mistakes. So what we now can do then also is to add that scenario for her. Let's add that. Okay. So the scenario for her is this one here, right? With those three presentations. So we have the three presentations, that dull, aching, and nagging. So in the file, it's a long scenario. So it is an and-ing conjunction of her pain being an I of P yesterday. The pain occupies her pain period. Her pain period is a satisfiable period during the entire time. There is a part of her pain which corresponds to a temporal part of her pain period and so on. So all that is expressed here. And here we also say that there is, of all the parts of her pain that she has, okay, it's always one of those three pains, okay? So the difference with these parts here we describe three different specific periods, okay, which are belong to a specific pain type, okay? But that is not enough, okay? If you look at the axiom that we set here, okay, all the parts need to be such that they are of one of those three types. So that's why you also in the scenario need to specify this. So, and if that is the case, then we can test the theorem. Okay, I'm checking it here. So under this scenario, her pain should be a PIFP yesterday. Okay. Let's try that. And the more axioms you have, okay, the more rules that are generated. And usually it takes also longer for a theorem prover to find the answer. But there you go, it has it. See, it required actually 60 steps out of very many, and a lot of axioms, okay, from the BFO and from our little ontology that play together to actually demonstrate, okay, that the pain that we described of that lady satisfies the requirement for being a PIFP. Voila, that is what I wanted to show you. We are at the end of this presentation here. Are there any very last questions? No? Well, then I hope that I have been successful in demonstrating that it is worthwhile to use first-order logic to develop ontologies in combination with the right tool. And I do hope that I did not scare you away. All right, bye-bye. If you have any questions, you can always send me an email afterwards. Enjoy the rest of the bootcamp.
Thank you. This is very cool.
Thank you. Where is it?